So very warm welcome, everyone. We have today Rami Jreige for our Cosmos virtual lab. He will present today model use in dark matter detection and experiments. Thank you very much, Rami, for being here today.
Thank you, Sylvia, for accepting having me present my work here because sometimes it's such a niche field that it's nice to be able to present it to people who work on something similar. So today I'll be presenting really about the notion of models and how they're used in dark matter detection experiments, because these kinds of experiments haven't really gained a lot of philosophical attention, despite I think the fact that they should. And I think one of the main reasons is that they haven't really given us any concrete evidence to either verify or falsify the existence of dark matter. And for me, that's really what makes them so interesting. So, kind of following a bit on the article, how I wrote it, I want to start off with kind of presenting a taxonomy of theories and models, because I feel that it's much easier to understand what goes wrong or where the problem lies once we have at least such a taxonomy to talk about. And this is mainly taken from, a combination of two articles, one by Antonio and about what is data models, and one by Caraca from 2013 about the difference between background theory, theoretical model, phenomenological model. But they all are about particle physics, which is why there's some differences here. So, first is the background theory. This is one that provides abstract relations and the properties required for their interpretation. And these are conditions imposed on a chosen mathematical structure used. In our case, of course, that's non-Euclidean geometry. You have GR, which is just relates the mass to the shape of space-time. But it doesn't say anything more than that. It tells us nothing about what exists or what the universe is supposed to be like. And this is where the theoretical model comes in. This kind of model is one that's bound by the background theory, but it introduces the domain of objects that provide constraints. So in our case, of course, the universe can also include the standard model of particle physics if one likes. And in the most recent iteration, of course, lambda CDM, a cosmological constant called dark matter. And then we have the phenomenological model. This is one that introduces a particular state of affairs, so for example, the Milky Way galaxy, to specify more precisely the interactions that are needed and the situation at hand. So if we're in an Andromeda galaxy, the distribution of dark matter where we are would be different than where we are in the Milky Way. And if we were further out or further in, that will also change accordingly. And next we have the experimental model. And this is one that I really want to focus on in this talk, because this model is based on the specifics of an experimental setup whose interactions are known. And it doesn't necessarily have to have the same background theory or theoretical model as the phenomenological one. Now, that is the case with particle physics experiments, but that's not the case here. And next is a data model. Now, this I won't talk about much, but it's included there because it's, of course, necessary, because this is how we get the results of the experiments. However, it's just important to point out that it's always constructed in a way, as many point out, so that it can communicate with the experimental model, of course, a phenomenological model, to compare and contrast. Now, the one thing we have that's common among this, at least in the way I'm presenting it, is the notion of constraints. Each, let's say, level in the hierarchy or taxonomy, because it's not exactly a hierarchy, adds constraints on the other one, so that at least at the experimental model level, we can compare the different constraints. And there we go, sorry. And we have the need for autonomous constraints, because really the history of GR and lambda CDM, at least as I'm going to present it very briefly, shows us this. So in my article, I go into a bit more philosophical discussion as to why this is a necessity, but at least for the purposes of the presentation, I'm just going to go into really the history of GR and how we arrived at Lambda CDM to show how the constraints are autonomous. So start off, general relativity as a background theory is conceived independently of cosmology. There was no lambda in the first iteration, the first publication, because it had nothing to do with cosmology per se. It was just about exploring gravity. But then Friedman pointed out that the correct treatment of Einstein's basic equations leads to a class of expanding, contracting universes. In other words, it was impossible to have a static universe with GR without lambda. Given that at the time it was assumed the universe was static, Einstein had to include the term lambda begrudgingly to stabilize dynamical models of GR. Hubble then discovers that the universe is actually expanding, and lambda turns to 0. And it's kind of interesting to see how the background theory keeps changing according to the theoretical models that we come out. This, however, is a very particular feature of cosmology that I'll come back to in the end, because this doesn't happen in the rest of physics. And very simply, it's because the model, the theoretical model that this is kind of contrasting with, the Big Bang model, it's unique. In cosmology, it's a unique model. There is no possible universes or how the universe could have possibly behaved. It's one universe, it behaves this way. Can GR account for it? Yes. It good. No, we have a problem. And this is then we go to Lambda CDM. So Lambda CDM came about in 98 after discovery of the accelerated expansion of the universe, which meant that we now need lambda to be positive. And then there was many other observations that kind of pointed towards the existence of CDM, for example, galactic rotations, inflationary cosmology. And then we have really Big Bang model and Lambda CDM. But as they are, despite changing the background theory, they provided little to no constraint on what dark matter is itself. I mean, the range is massive. It's from 10 to the negative 1 eV up until 10 to the 21 eV. And really, by any theoretical standard, this range is incredible because, originally it was much smaller, but then it kept expanding because there are no constraints on it. There have been attempts, there's even been attempts to try to find it in the Large Hadron Collider, all unsuccessful. Now, the phenomenological model for our case would be what's called the standard halo model, and it's a Gaussian velocity distribution of dark matter in the galaxy. Of course, this is again based on many assumptions. So we have, based on the distribution of visible matter, we can get an idea of the shape of really distribution of dark matter and their velocity in the galaxy. And of course, we're assuming dark matter particles are non-self-interacting, which means they're evenly distributed. It's an isotropic homogeneous sphere. And kind of just from this very simple view of these three levels, we can see that the constraints have to come from outside the hierarchy. But when they don't, such as in the case of a logical model, we have a lot of assumptions coming in. And add to that, the mass itself is unconstrained. It's going to be really hard to tell and to know what happens when we experiment, to be able to interpret the experiments correctly. And in our case, the experimental model, in contrast to particle physics, is completely independent of the background theory, the theoretical model, and the phenomenological model. In fact, the background theory of the experimental model of differential event rate is just standard non-relativistic quantum mechanics. It's nothing more than just regular scattering. And more importantly, it's a model of the detector itself, namely that the target material and its known interactions. So we construct the experiment, we know what the material is, and because of that, we know what its interactions are or how it's supposed to interact based on different masses. Now, very briefly, the experimental model in this case is the differential event rate. And as you can kind of see use the mouse here, quite briefly, you have a lot of dependence on the target material, which we know, but then you have a lot dependent on dark matter, which we don't know neither the mass nor the distribution, but we can assume it, and neither do we know the velocity. And in addition, because of the way these experiments are constructed, this is only dependent on the minimum velocity that can produce a recoil in the detector. So this means that it's indiscriminate in terms of velocity, no matter how fast or slow, well, as long as it's over the minimum velocity, it should give us detection. But that minimum velocity is dependent on the materials in the detector, which gives us the minimum energy, which means we have a very strong dependence on what's in the detector. And very simply, detection experiments are particles placed in a vat, put underground to minimize interference, and then we wait. And this is the results from Dama Libre phase 2. So the residuals is the detections per kilogram per keV, and then the time is per day. So phase 1 was the first 10 years, and these are the second, I think, 3-4 years here in the first phase of it. And you can see sinusoidal, of course, because assuming the sun-Taylor model, as the Earth goes around the sun, sometimes it's heading into the dark matter wind, sometimes heading away from it. And the construction of this graph, of course, is based on the assumptions that we have, but we do get detections. Dama has that. However, it's difficult to have cross-experimental comparison. Lux, another one, has had no results. Super CDMS had results. Some Super CDS or Cogent, respectively. Some detectors have had results. Some detectors have not. The question really becomes is, how do we compare them? If going back to differential event rate, I mean, there is a strong dependence on the velocity, minimum velocity, which is dependent on the recoil energy. And the recoil energy is dependent on the target material. So in Lux, it was liquid xenon. In Dama Libre, I think it was sodium iodide. So, no, it's not sodium iodide, respectively. The point is that there's a strong dependence on the target material. And if there's such a strong dependence on target material, then how do you really compare the results of two different experiments? And that's where the difficulty lies. Because to make any graph requires some assumptions. Either we assume the mass and have a sigma velocity plot, or we assume the velocity, have a mass sigma plot. But in both of these, there's massive problems. So you have the range of mass is from 10 to negative 21 eV to 10 to the 21 eV, and the velocity is under 320 meters per second, the galactic escape velocity, which is itself an assumption. And this is really where the problem lies, and there have been many attempts to try to counteract it. For example, as I mentioned in my article, Fox Italia, they had the rescaled velocity integral to try to kind of find exclusion zones, right? So two experiments can at least tell us that the particle is not in this zone of mass velocity. But again, there are so many problems with it that it becomes more and more difficult to kind of account for it. And with such a heavy dependence on the experimental models and the experimental models really, then the question that really I want to ask and point out is, well, do we know? And do we need to separate models for cosmology? Because contrast it with particle physics. So in particle physics, for example, the Large Hadron Collider, we know the initial conditions of the particle and the initial conditions of the detector. And in this case, of course, that's how we have a signature for the particle in particle physics. But in cosmology, our initial conditions are really dependent on the models we have. So any change we assume to be of the initial condition of the particles means we have changed the models. And the moment we change any of the models, we've changed initial conditions of the particles. So epistemologically speaking, in cosmological experiments and cosmology in general, our knowledge just comes from models, mainly. We can have some experimental results, some autonomous constraints as presented by some um, uh, different experiments. I forget them now. Um, to constrain, for example, distribution of DM in the galactic neighborhood. But more often than not, we're reliant on models. And this is something I wanted to mention that I mentioned earlier about the theoretical model Big Bang is that it's unique with a unique history. And we're trying to discover this unique history from what we have now. So we're relying more and more on models. So whereas in particle physics, many philosophers have pointed towards the theory lateness of experimentation and the circularity. It's different. In particle physics, circularity has been between the phenomenological model and the experimental model. This is the one that Caracas' article tries to explore, and more recently Falkenberg and quite a few others, namely that the background theory of the experimental model is the same as the phenomenological model, because I mean, these are the most basic kind of ideas that we have to use. In cosmology, however, the circularity is between the background theory, the theoretical model, and the phenomenological model. Whereas the theoretical model for particle physics is a standard model. It's about types of particles. Whereas the theoretical model for cosmology, it's about a unique object, the universe that we have. And there is really no way around it. We cannot hypothesize what if the universe was differently, what we get. We can just try to figure out how the universe is now. And the phenomenological model is highly dependent on that. So kind of this is what I want to explore a bit, and this is kind of what I want to conclude on to open kind of a bit more discussion on it, because this is what came out of the article at the end and what I'm working on now, is that we need a more generalized notion of models for cosmology that are separate from really anything else in physics. Because the Big Bang is a unique universe with a unique history. I mean, the Big Bang model itself, the theoretical model, can function as a phenomenological model when experimenting cosmological hypotheses, for example, the cosmic microwave background. We see it as well with the freeze-out time experiments that happened, I think, in the 80s or 90s, the Big Bang nuclear synthesis. So we kind of see this quite often, that the theoretical model in cosmology can also act as a phenomenological model, depending on what we're working on. So the lines tend to be more blurred. But because of that, they also tend to be much more circular. This is why I'm kind of been toying with the name cascading models, because the moment you change anything, everything cascades. So with GR, we add lambda. Now we have static models. We figure out the universe is dynamic. Lambda turns to zero. Then we find out the dynamicity, the acceleration of the universe, the expansion of the universe actually accelerating. Lambda turns positive. And with that, of course, models of structure formation, of inflationary cosmology, all of that changes every time we change any single thing within these three models. And so, for example, with cold dark matter, if we find primordial black holes as opposed to cold dark matter, superfluid dark matter, or really any of the other alternatives, then everything else is going to change. Some things might stay the same, for example, the age of the universe or some part of inflationary cosmology, but then we have to find a way to account for galactic rotations, for example. Um, so this is kind of the idea I'm toying with at the moment, and I'm hoping to have a bit of discussion about it here, is the notion of,
Yes,
do we need separate models of cosmology? Do we need separate models just for cosmology? And in such a case, well, how do you go about it? Because the experiments themselves, even so, in philosophy, there's Jamie Elder. I've recently seen her articles about the EHT and gravitational wave detections, which kind of have this problem also with circularity to a certain extent. that's different than particle physics. And yeah, I just want to open the room for discussion more than anything about, you know, what you guys think about it, and is there really a need for separate models in cosmology, and how to go about it. Thank you.
Thank you. Thank you very much for your presentation, which was actually very very quick. And so can you stop sharing the screen? Because otherwise I see my face.
Yes.
Okay.
Sorry.
Not that beautiful. Okay, so thank you very much. And so your presentation was very effective, very short, but full of references, of course, to further discussion that can be implemented. So I don't know whether Marco or Federico or Nuria have questions for you or remarks. Yes, please go ahead, Marco.
Hello, just a quick check. Can you hear me fine?
Yes.
Oh, perfect. Thank you. Well, thank you very much for the presentation. I do have like a couple of clarificatory questions rather than full discussion, honestly. So you draw a parallel with, or at least you use high energy particle physics as like a comparison to an extent with respect to cosmology, and you say that. So I understand what you mean when you talk about the circularity problem in cosmology and the cosmological models. Yes, the fact that the universe is a single object, we do not have any other universe we can compare our universe to, makes, for example, the whole statistical sampling impossible, and so on and so forth. I do not fully understand but you compare that with the circularity in high energy particle physics, and I don't understand what you mean by that. Like you say that they are different, but I don't understand the one in high energy particle physics. I know it's not the topic of the talk, but I don't understand entirely the comparison if I don't understand one of the two terms. Could you say a little bit more about that? Maybe I'm just not familiar with the literature.
No, of course, of course. Yeah, sorry, it was a bit too quick. Sometimes I have a tendency to do that. And so in particle physics, generally, at least the sources that I'm mentioning about theory latedness and circularity, one of the things they constantly mention is that the background theory of the experimental model is the same as the background theory of the other models. So the way the experiment's set up, I mean, if you're having a background theory in terms of, let's say, scattering in high energy physics, right? The theory that tells us what scattering is and how it behaves is the same theory that we're testing out.
But
The
you're
background
testing a
theory, at least.
model. You're testing an hypothesis in
Yes.
a certain. For example,
Yes.
yes, you want to test like supersymmetry models. Sure, you want to look for new particles, supersymmetric particles, and in order to do that, you need to crash protons or like have like new jets and whatever. And the physics and the theory that tells you how to create those jets is basically quantum field theory, or the standard, or at least the basis of the standard model of particle physics. But you still test another model or something that goes beyond your current model. So I don't like, I'm testing supersymmetry, which is a beyond standard model that has quantum field theory as the background knowledge in a sense. But there's a distinction between the theory in that sense and the standard model of particle physics. It seems to me.
Well, yes, but now we're going beyond the standard model,
Yeah,
right?
yeah, yeah. Sorry, yeah.
And in the early stages, for example, testing for the Higgs boson, really, I mean, you're just testing the standard model at this point, and quantum field theory, which is going to be the basis for you for the experimental model, which is also kind of the scattering. You're going to understand the scattering, what's going on. You're using that as well for the experimental model. So that's where the circularity or the fear of circularity was present for high energy physics. Now, according to Karaka and then Falkenberg and others, it's a weak circularity because, exactly as you said, right? You're using one part of quantum field theory to test a model from something different in quantum field theory. And so it's a weak kind of circularity that is not vicious. But the circularity that's always pointed out is between the experimental model and the phenomenological model.
Well, the one in cosmology is different.
Yes.
Now I see that. Now I see the comparison in that sense. Sorry, maybe I missed that. Sorry. Thank you.
Yeah, but that's where it happens, is that whereas in high energy physics, we know the initial conditions of the particle we're testing. In cosmology, for cosmological experiments, we don't. Which means the only thing we have to go off to understand what's going on is the models themselves, which are assumptions based on assumptions. So a simple example where this succeeded is LIGO, right? We detected gravitational waves, but then the reason we know we detected gravitational waves from black hole mergers is because we already have a model of black hole mergers that tells us what the gravitational waves should look like.
Yeah, okay.
So once we get that signal, the experimental model is not a problem, right? It's a very simple kind of, I mean, I say simple, engineering-wise, it's extremely complicated. Michelson and Morley kind of style experiment with lasers on a massive scale. But once you get the signal there, then to interpret the signal, you're using the basis of the model to try to show that the model exists. Because you're using the signal you expect to get from black hole mergers to show that black hole mergers exist.
Yeah, that makes sense. Okay, yes.
When it comes with particle detection, because we're trying to show that the particle exists, this fails. Because now we're assuming the existence of dark matter, we're assuming the function is a certain way, and we're getting a detector. But then with LIGO, we don't need cross-experimental detection. With DAMA, with all the other experiments, well, now the dependence on the experimental model becomes stronger. And then the question is, well, how do we interpret the experimental results with such a massive mass range and a massive velocity range? So to give a simple example, the successor of Dama Libra is called Xenon 1T. It's also in Gran Sasso. And one of the initial results from that was interpreted by a couple of physicists as showing the detection of dark energy, not dark matter. So the results are really open for interpretation because the initial conditions of the phenomenological model we're using is just based on assumption after assumption.
But wouldn't you wanna look for models, like build models that are not that sensitive to changes of initial conditions?
But how do you do that? That's why, for example, I pointed out briefly in my article, but the problem is it's so massive right now. You find a lot of what physicists are trying to do called model-independent methods in physics to try to interpret the results of the experiments independently of the models. Like if you go on arXiv and just type dark matter detection and in the model-independent methods, you'll get thousands upon thousands of results that are still going on to this day because they're so model dependent. But of course, there's no specification from the physics side. That's why I think we need to understand that models and cosmology to be different. They're so model dependent that depending on how you interpret it, you can either kind of entrench the uncertainties from the experimental model, or you can entrench the uncertainties from the theoretical model.
Yeah, so I can continue, but I think Federico had a question, maybe, didn't you?
Yes, Federico.
Otherwise, I'll ask after.
Actually, I had a similar question to Marcos about if you could clarify a little bit the threefold circularity we have in cosmology. Now that you answered a bit, I think I have a new need for clarification, which is about what you mean by initial conditions in a cosmological model. Because so do you mean initial condition of the universe, or do you mean initial condition from which we could both predict and retrodict the evolution of the universe. Because in the second case, it's not so evident that they are, entailed by the model because they are derived from observation as well.
So in the case of dark matter detection experiments, the initial conditions is simply the mass and the velocity. So so after scattering happens, right, in the detector and you get detection, well, you know the target material, and you know you got scattering of a specific energy level. Well, how do you recreate? How do you know what the mass is if you don't know what the velocity is?
Mhm.
So this is the specific case of dark matter detection, and kind of I want to expand this kind of idea to cosmological experiments, because you say they're from observations, but if you I've been going into this more and more. If you look at all these observations and how they're interpreted based on the theory, right? So with any change of theory, like 1998 with the accelerated expansions, a lot of these different observations have to be reinterpreted.
Okay.
Right, or for example, more recently there was a PhD student in Spain who found large galactic structures that showed that the universe might be older than
Mhm.
what we now have it, and that's causing a kind of, we're going to have to reinterpret all the observations we've done, because in
Yeah,
cosmology, sorry, yeah,
no, that's fine. Maybe um, my answer is more about my question is more about okay, so how we interpret observations is model dependent, but I don't understand why you say initial conditions are model
Mhm.
dependent. Because more than in the case of dark matter. That was my question.
Yeah, it's in the case of dark matter more than not, because in the case of dark matter you have clear initial conditions, mass and velocity, but those are dependent on the models you take of the galaxy. You change the standard halo model, as some physicists have done. You change the initial velocity, or what's the upper limit of the initial velocity. You change the theoretical model from cold dark matter to something else, and you're changing the initial conditions of the mass that you're trying to detect. So that's why they're dependent on models. And I compare it to high energy physics because we know what the particle is that we're sending out, that we're accelerating.
Okay. I think again. Thank you.
Does that make sense?
Yeah. Yes. I mean, for me, it's always tricky to to understand in cosmology what we mean by initial conditions, because sometimes it's about one speaks about the initial condition of the universe. Sometimes it's just connected with observation. So I just wanted to clarify which of the two,
Okay.
but I think you're more now I understand you're more on the second side.
Yes, I
Okay.
am.
Thank you.
Marco, did you have a follow-up for the previous question?
No, actually, I feel like what was discussed here kind of helped me clarifying a little further. Actually, no, I don't like then. I'll move to the last question. Sorry.
Yeah.
So you talk about you talk about separate models, right? Like the need and the search for separate models in for dark energy and dark matter. Like I don't fully understand what you mean by a separate model. Like autonomous models, like like could you tell me
Okay.
what like a separate model would look like?
No, sorry. Maybe I kind of used it a bit wrongly. I don't mean separate models. I mean kind of the modeling. So in philosophy of physics, when we look at, let's say, when people discuss models and how models are used and their function, they tend to be about high energy physics. And what I want to say is that we need to have a separate discussion about models for cosmology itself, because cosmology really is a very different kind of beast to deal with than high energy physics. And I think there's sufficient unique parameters or properties of cosmology that it requires a separate discussion on models because the ones from high energy physics, I mean, the way they function, the way they behave, I mean, the whole discussion of model representation in science and physics that you find is centered around high energy physics. And any kind of extrapolation to modeling practices in cosmology, it's not working. Or at least if I've tried, or from what I've seen from philosophers of physics, it doesn't work to the same extent. That's what I mean. I mean, we need to kind of separate in philosophy of physics the way we deal with models in cosmology and the way we deal with models in particle physics.
Okay, sorry. Then makes much more sense, because at first I thought that you wanted to like separate models in a sense from the theoretical background, and I was generally not like curious about how you would do that. I was like, but that makes much more sense. So you
No,
don't
okay.
want the interplay between cosmology and particle physics in the context of the discussion in philosophy of physics.
Yeah, I mean, not so much. To a certain extent, there is, but at the same time, it's important to understand that the way we use and construct models in high energy physics is sufficiently separate from cosmology, right? So I've noticed a lot of philosophy of physics discussion these days have turned towards kind of thermodynamics and inflationary cosmology with regards to thermodynamics and what's it called? The Boltzmann paradox of thermodynamics of the early universe. And I've noticed a lot of philosophers of physics, when they talk about kind of these and the possible different models and how to escape this, the modeling of the cosmological modeling taking place is quite similar to high energy physics, but high energy physics is quite different for the reasons I mentioned. And that's why I think we should have a study at least of modeling practice in cosmology itself.
No, I agree, especially because
Yeah.
the actual practices done by the practitioners, like that, like not philosophers of physics but scientists, are indeed quite different.
Yeah, because they have different problems, like I mentioned. So, for example, now in dark matter detection experiments, at least from what I've seen from arXiv, so many are trying to find model-independent methods, or trying to find some alternative that could also explain some of the results we got, or maybe lack of results we got, because in the end you're relying on experiments to verify what your theory is. And when it becomes more difficult to do so, well, then the question is, how do we do it? In high energy physics, you have beyond the standard model and supersymmetry. In cosmology, on the other hand, you can't even find a way to verify the models that you have now.
Yeah, thank you.
Okay, so are there other questions? Okay, so, well, if not, well, I have actually a general question for you. Did you present this work to a scientific audience before? What was the, let's say, the reaction, so to speak, to what you say?
No, I haven't presented a scientific audience before, because I'm generally, but so my background's in physics, but my PhD was in philosophy of math. So the more connections I have are from, let's say, the mathematical community, not the physics community. And this is the one, let's say, something that's completely in philosophy of physics that I do. And I've been trying to more engage with philosophers of physics and, well, physicists, if possible, to see what people think and how they react. Because as of yet, there's no really philosophy of cosmological experiments, or very few.
Yeah, no, indeed. But I was just curious, because of course, physicists would have much to say with regard to your analysis on current, missions, experiments, and so on. And would have been interesting to see whether they perceive, for example, the same, I mean, whether they share your definition of data model and experimental model and so on, and their interplay in the same way as you do. So that could be interesting, actually. So yeah, that was just yeah, my question. Okay. So If there are no other questions, we thank our speaker. It was the quickest seminar that we had this year. And Rami, of course, you are more than welcome to join our network. If you like, there is a contact form. And thank you all for the discussion.
And thank you for having me here. Yes, I'm glad I set a bit of a record, even if it was not good. You know, being in France, there's people tend to talk too much, so I've always tried to shorten as much as possible my presentations, sometimes to a bit of negative effect, but c'est la vie. Thank you again for having me here.
Thank you. Thank you. Bye-bye. Bye, guys.
Bye.
Bye, thank you.